Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 4-3 lesson on logarithms. This is an intro lesson to logarithms. In this one, we're going to figure out what logarithms are and how to simplify expressions with logarithms.
For the warm-up, let's see how much you remember about logarithms already. Let's say we have log base 3 of 81. What does that mean? What's the value? Pause the video and see if you can figure it out. All right, let's see what we came up with. This is asking the question, 3 to the what power equals 81? Well, 3 to the 4th power equals 81. So that means log base 3 of 81 is 4. So a logarithm at heart is an exponent. It's the exponent you have to raise the base of the log to get the number inside, which we can call the argument. Now there's two different forms we're looking at here. This first form with the exponent is called exponential form. And this other form with the logarithm, big surprise here, logarithmic form. So exponential form in general, you have some base to a power equals a number. Logarithmic form, you have a log of this base that's over here of the thing that this exponent equals, and this all comes out to equal a power. Now that we've reviewed the definition of a logarithm as the exponent that you have to raise a base to get the number inside, try these problems out on your own. Pause the video and give it a shot. All right, so for this first one, we have to raise 7 to the 2nd power to get 49. This next one, we don't see a base down here, so if we don't see a base, there's an invisible 10 down there. Log is really log base 10 by default. So the power we have to raise 10 to get 100,000, well, we just have to count the zeros here. That's going to be 5. Now, those of you who got a weird decimal when you tried taking log base 3 of 81, probably were just plugging it into your calculator. Your calculator's log button is the base 10 button. So you have to be careful and make sure you're actually using the correct base. For this next one, we have to raise 10 to the 0 power to get 1. In fact, log base anything of 1 is going to be 0 because anything to the 0 is 1. Over here, we're asking, what do I have to raise 10, or really any number to get 0? There is no exponent that you can raise 10 to get 0. You can't multiply 10 by itself and get 0. So this is going to be undefined. And if you remember back to what logarithmic functions look like, you might remember that there is actually an asymptote at x equals 0, vertical asymptote. For this one, we're asking, what do I have to raise 10 to get negative 10? Now, again, there's nothing you can raise a positive to get a negative, so this is also undefined. And you might remember from the graph of logarithms that the graph is completely undefined. There is nothing for the function to the left of the y-axis. Here's a few other kind of oddball cases. Try these out for a second. So this one, we're asking, what do I have to raise 6 to get 6 to the 10th? Well, this one's so easy, it's hard, right? To get 6 to the 10th, I need to raise 6 to the 10th. So what ends up happening here is your log base and the exponent base actually end up canceling. If they're the same thing, they cancel. So that's just 10. Over here, this is ln, not in. This is a lowercase l. This is the natural logarithm. So we're basically asking log base e of e to the 7th, which, looking at our case back over here, same base, those are going to cancel. That leaves us with 7. Try these next 4 out, and keep in mind as you do these that they all involve being able to rewrite the base with some kind of exponent. All right, let's see how you did. For this one, we're asking 3 to the what power is 1 over 243. Well, 3 to the 5th power would be 243. To get 1 over that, we need a negative exponent, so this is going to be negative 5. Over here, we're asking, what do I have to raise 7 to get the 9th root of 7? Well, the 9th root, remember, is just the 1/9 power. So this would just be 1/9, because the bases cancel out and we just get the exponent. Over here, we're asking, what do I have to raise 49 to get 7? Well, to get from 49 to 7 by exponents, we need to kind of take an exponent in disguise, the square root, and that is the 1/2 power. And then lastly, ln of 1 over 7th root of e. This is a little bit of everything rolled into one. So we're asking, what do I have to raise e to to get this stuff here. E right here is being raised to a negative exponent, and it's also a fractional exponent. This is going to be the negative 1 over 7. If you're feeling super ambitious, pause the video and see if you can wrestle with these on your own. All right, let's see how you did for this first one. So when we're raising 8 to a logarithm, the key here is to remember that logs are exponents. What we're doing is raising 8 to the exponent I need to raise this little base here, 8 to get 19. Let me write that out for you. This is 8 to the power I need to raise 8 to get 19. Well, let's read this a couple times. If I raise 8 to the power I need to raise 8 to get 19, then I'm just going to get 19. Another way of saying this is when you have a base raised to a log with the same base, because of this kind of circular reasoning up here, you end up getting whatever was inside that log that was in the exponent. So again, we have a situation where these bases of the exponent and the logarithm cancel each other out. Only instead of having an exponent inside a logarithm this time, we have a logarithm inside an exponent. All right, try the next couple problems out based on that. So here we have 10, and this is log base 10. Again, those are going to cancel, so this is going to be 33. Here we have e, and log base e cancels, so that's 25. And here, you might have been tempted to write 27. Oh, but careful, look, we've got third base here. So we can't just go ahead and cancel those out. The bases need to match in order to cancel. So instead, let's actually evaluate this logarithm. What is log base 3 of 27? What do I have to raise 3 to get 27? Oh, well, that's the third power. So this is really 2 to the 3 power, which is 8. We're going to wrap this lesson up with a nice little aha moment. So take a sec and see if you can find the inverse for y equals b to the x. You think you got it? First off, does it have an inverse? Well, it's an exponential function, so it passes the horizontal line test. Since it has an inverse, we can switch the x and the y values with each other. So we can rewrite this as x equals b to the y. And now we always have to isolate the y when we're finding the inverse. So how do we get y not in the exponent? You might remember at the beginning of this lesson, we had an exponential form and a logarithmic form. If this is your exponential form right here, we need to convert this to logarithmic form. So remember, the base of your exponent is really the same thing as the base of your logarithm. This y here is the exponent that equals the logarithm, because logs are exponents, and this x is the argument inside the logarithm. So this is really y equals log base b of x. Now take a second and look at where we were and where we are now. Exponential functions and logarithmic functions are inverses of each other. Just to show you what's going on graphically, here's your exponential function. And if we reflect that over the line y equals x to get the inverse, because we're switching the x's and the y's, this is your logarithmic function. Notice that we have a vertical asymptote right here on the y-axis. And we can't get past the y-axis for negative inputs. So the domain of logarithmic functions is going to be all x's greater than 0. And then the range of logarithmic functions, we can go down forever, and it's a less steep slope, but if you go far enough, you can go up forever as well. So your range is going to be all real numbers. And remember, this is the exact flip of what you have with exponential functions, where your domain is all reals and your range is just the positive numbers. So that's it for now. Hope you enjoyed our eye-opening moment here. Until next time, this is Mr. Sutton, logging off.